Okay, so here we go. This time with the transshipment problem. This is also another way to model transport. It's actually a very similar problem to the transportation problem. And of course, it's very important in logistics. I'll begin by just reading the prompt. That way you'll see the little difference. So consider the following scenario. There are M suppliers, each with a supply Si, and there are also N retailers, each with a demand of Dj. So here we understand these parameters just like we did for the transportation problem. The suppliers, they just represent factories or anything that is a source of product, and the clients are going to be the end consumers. So essentially, we are to find the course of action. We are to find the quantities that must be sent from the warehouses, from the suppliers to the clients in a way that we satisfy their demand while minimizing the cost. But now there's a difference. It's not like the transportation problem because there's also a set of transshipment points. And I'm just going to assume that there are Q of them, okay? That will be useful later. Okay, once again, we always know the shipment costs, and we are to write an LP formulation, a linear program, okay? So how do we tackle this? I say we begin the same way I always do, which is making a digraph representation of the setting. So on the left side, I draw a set of suppliers, and I'm just gonna label them like this up to M. We said M of them, right? Yes. On the right side, I'm going to, maybe I'll make a note, suppliers. On the other side of the sheet, we're going to represent all the clients, 1, 2, up to N, right? Yes. Clients. We know that on this side, each of the suppliers has a total stock, a total quantity of S1, S2, and up to SM. And we also know that the demands are D1, D2, up to Dn. Okay, this is nothing new. This is all the same as in the transportation problem. And now, the special part comes when we introduce the transshipment points. These are essentially intermediate locations through which we have to go. And of course, there are more generalized versions of the problem, but this time we're going to assume that everything that gets sent from the suppliers to the clients has to go through exactly one transshipment point, okay? So let's just draw them all. I said Q of them, so I'll just draw a couple, right? 1, 2, Q. Okay, and you can see how there are so many different decisions. Like supplier M can send products to so many different transshipment points, and then from each of those transshipment points, the products can travel to each of the clients, right? In total, there would be, I would say, M times Q arches over here, and Q times N over here, because we're allowing all arches to exist. Okay? Yeah. And for each of these arches, there's an associated cost that we do know. Okay, and maybe I'll just represent them like this. Yeah, maybe we can call them CIP. It's cost of going. Actually, I say going, but I mean of sending 1 unit of product from supplier I to transshipment point Q. Transshipment point P, right? And this, of course, would be defined for all I and M, and for all P and Q. Well, this notation means all P in 1, 2, 3 up to Q. Okay. Of course, this is only the costs of these arches, so I'll just make another variable, and I can label it with another letter. I don't even know. I'll just use O. O from P, and I'm just going to use letter J to represent cost of going from the transshipment point P to client J, right? And like before, I would define this for all P and Q. These are all the transshipment points, and for all J in up to N, right? Yes. So these are just parameters, right? But of course, we always have to formalize them with symbols. I've seen this problem solved a little more concisely by using a single set of symbols instead of C and O. I've seen it solved with only C, but I think it's more explicit if we differentiate the arches in this half and the arches on the other half. Okay, great. So now I'm going to finally move on to decision variables, right? Once we have the parameters, the next thing, it's the decisions. And in this case, the decision variables are almost exactly the same that we had in the transportation problem. The only difference is, once again, that we have to separate them into halves, just because it'll be necessary when we're writing our objective function. In this case, I would do xip to represent the number of units sent from I to P, right? And you can see I'm labeling suppliers with I, I'm labeling the transshipment points with P, and I'm labeling the clients with J, right? Just to be clear. That way I don't have to write it over and over, right? And that's this. These variables only represent this half. We would have to add another set of variables to represent how much you're sending along each of these arches, right? And those would be Pj, right? Similar definition, number of units sent from P to J, right? Besides that, there's nothing else. Like if I told you the values for all these variables and the values for all these variables, you would immediately know what's the course of action. There's nothing else to know, really, right? So let's move on to the objective function, right? In this case, we clearly stated that our goal is to minimize the cost of satisfying all demand, right? Well, those conditions, the conditions to satisfy demand, will be imposed by the constraints, which is the next part we're going to do. But for now, all we have to say is that the cost we incur is directly related to how much we send along each of the arches and at which cost, right? I don't know if that was clear, but I'll write it down so that it's obvious, right? We have a minimization problem, of course, and then what we're gonna do, it's two different summations. And I know this might seem a little confusing, and I apologize for introducing two sets of variables. But I think it's technically more correct, okay? So in this case, you can see how the total cost of sending units from the suppliers to the transshipment points is going to be given by multiplying all the quantities you send times their respective costs along the arches that you're sending them, right? You would make this summation for all possible arches, right? Right. So it would be from 1 to 1, 1 to 2, 1 to each of the transshipment points up to 1 to Q, and the same for all the other suppliers, right? So for all i's from 1 to m, and for all p's, p equals 1 to q, right? You're going to add them up, right? That's the first half. The second half would be this side over here. And the strategy is the same, so I'm just going to do it here. You would add up the quantities that you send. Whoops, maybe instead of x, I need to use y this time. ypj. And then from p equals 1 through q. And then j equals 1 through n. And that would give us exactly the cost of the course of action, right? But of course, if we stop here, the minimizer will just find a zero objective cost. And that's because we didn't say we have to meet the demands. If we want the actual program to work like we expect it to, we need to actually impose some constraints. So let's do that. Constraints. And there are a few sets of constraints, but they're all very simple. Basically, everything boils down to flow balance and supply and demand, right? So let's just say the very first thing. So supply and just supply, right? Supply constraints. These constraints are going to represent the fact that we can only send up to SM from this node. For each of the suppliers, there's a limited supply. So we need to make sure that the addition of all the units sent to each of the transshipment points doesn't go over that limit, right? And the way you do that is as follows. Supply constraints, you would need to add the quantities sent out from each of the suppliers. It would be from I to P, okay? But then you would only add it for all the different transshipment points. So for example, if I is equal to 1, it would be x11, x12, x13, x14, up to x1q, right? And that would tell you exactly how much you are sending out from 1, right? If you specify that this has to be less than S1, in the general case Si, then you are limiting the supply. And that's what we want to do, but not only for 1, but for all the different suppliers, just up to M, 1, 2, 3, up to M. Now, a similar constraint is the demand constraint, but this is actually the opposite. We talked about this in, I've made another video on the transportation problem, and it's the same idea. Here we just need to make sure that everything received, right, at a specific client, J represents clients, P represents transshipment points. Everything received at a specific client must be, so the sum of everything that arrives at the client has to be at least the demand of that client, because we are required to meet demand. So if we do the sum from P equals 1 up to Q, these are everything that you send from any of the transshipment points to the client J has to be at least the demand that the client J has. We impose this constraint for all the different clients up to n, and we make sure that that constraint is fixed. Okay, and then this is the same thing we did for the transportation problem. The additional constraint that we need to add now that we have transshipment points is something called flow balance. And this is essentially making sure that nothing gets stuck at the transshipment points. We're assuming that everything we send from the suppliers goes straight through to any number of clients, right? So anything that comes in must go out. And the way we do that is actually very similar to what we've been doing, okay? So I'm just gonna call them flow balance. And the way you would represent them is like this. I'll say everything that goes into P, right? And P represents just one of the transshipment points. How would we represent that? It's basically the same variable we had earlier, but instead of adding up the transshipment points, we add over the suppliers. So it'd be from I equals 1 up to M, right, of XIP. That's everything that goes in must be exactly equal to everything that goes out. And everything that goes out is once again the addition with a fixed P, right, with a fixed transshipment point, but for all the clients. Instead of all the suppliers, it's for all the clients. And we use this older variable, ypj, right? So it'd be like this. ypj, and we add over all everything that goes out. So from a fixed P, I send out to j equals 1 up to j equals n, right? And what I'm claiming is that they must be exactly equal for all possible transshipment points, P up to Q. Oops. Right. So that would make sure that everything that goes into here from any number of suppliers equals everything that goes out. And that is basically it. The only thing we have left is making sure that none of these variables become negative, because flows that go out of or into clients or suppliers must always be positive. So I would just do XIP greater than or equal to 0, YPJ greater than or equal to 0. And this is, of course, for all P, for all I, and for all J. Yes? And I think that's clear enough. Okay, then maybe I'll make some other examples in the future, but I think that's good for now.